In our last lesson, we were reminded that a distance is always measured on the perpendicular. So if a radius is perpendicular to a chord, then it bisects the chord. If the radius of the circle bisects the chord, then it's perpendicular, which is the converse. And a perpendicular bisector passes through the center of the circle. In today's lesson, we are going to apply the relationships between congruent chords of a circle. If two chords of a circle are equidistant from the center, then they are congruent. In other words, given circle P, if PX is perpendicular to AB and PY is perpendicular to CD, where PX is congruent to PY, then AB is congruent to CD. If two chords of a circle are congruent, then they are equidistant from the center of the circle. So we're given circle O. If AB is congruent to CD and OE is perpendicular to AB, OF is perpendicular to CD, then we know OF is congruent to OE. Here in our example, we're given circle O. Segment AB is congruent to segment CD. And on the diagram in your textbook, it's marked that OP is perpendicular to AB and OQ is perpendicular to CD. So even though it wasn't directly given in the textbook, it is marked on the diagram, therefore we know that to be true. So I'm going to mark the diagram, and now I see I have congruent chords. If the chords of a circle are congruent, then they are equidistant. So now I can say that OP is equal to OQ, and then substitute the algebraic expressions that they gave me. If I subtract 4x from both sides, I get 8x minus 5 equals 19. Now add 5 to both sides, I get 8x equals 24. Divide both sides by 8, I get x equals 3. Therefore, OP is equal to 12 times 3 minus 5, or 36 minus 5, which is 31. In 10.3, we take a look at the arcs of a circle. We need to be able to identify different types of arcs, determine the measure of an arc, recognize congruent arcs, and apply the relationships between congruent arcs, chords, and central angles. Let's take a look at some definitions. A central angle has a vertex at the center of the circle. AOB is a central angle. The measure of an arc is in degrees and is the same measure as the central angle. The length of an arc is the distance from A to B. So in other words, it's the measure of the arc divided by 360 times the circumference. A minor arc is named with only 2 letters, the endpoints. A semicircle is a half of a circle, and it is also named with only 2 endpoints. A major arc is named with 3 points. It's greater than a semicircle, but smaller than a full circle. So in this case, ACD is the name of the major arc. You could call it DCA. At this point, it won't matter so much. In further studies, you'll see that it's always referred to on the counterclockwise. There are a number of theorems in this section. You can read through the theorems in this section on your own. I'm going to jump into the bigger picture of why we study geometry. Remember, we're looking to get away from because the book, my teacher, some external source told me to. Looking to get into more analytic reasoning, which is making generalizations. We won't be doing proof in this section, so I'm going to jump into a generalization. And this picture represents all of the axioms. If we have congruent central angles, then we have congruent chords and congruent arcs. So in other words, if you have congruent central angles, the arcs are congruent. If you have congruent central angles, the chords are congruent. If you have congruent chords, the arcs are congruent, and all of the converses are true. Thus, you have the biconditional arrow. So let's look at some examples. To find the measures of the angles in a triangle, given that the measure of arc AB is 96.50. That means the central angle is 96.50. And we know that all 3 angles of a triangle total 180 degrees. So when we subtract, we get 83.50, which is the sum of A and B. Since the radii are congruent, these angles are also congruent. So I'm going to divide that by 2. Angle A is equal to angle B, which equals 41.75. To determine the fractional part of a circle when the arc is 72 degrees, I'm going to divide it simply by 360 degrees, which reduces to 1/5. To find the length of an arc whose measure is 72 degrees and whose radius is 3, remember that the length is the distance. So I'm going to take 72 over 360, and if the radius is 3, that means the diameter is equal to 6, and the circumference is the diameter times pi. We just saw in the last problem that 72 over 360 is 1/5, so 1/5 times 6 pi is 6/5 pi. And for our final example, the measure of an arc, find the measure of an arc that is 7/12 of a circle. I'm going to use a proportion here and call that x. So 12x equals 7 times 360. And I don't have a calculator handy, so I'm not going to multiply that through. Instead, I'm going to reduce. 12 goes into 36 3 times, so it goes into 360 30 times. That means that x is 7 times 30, or 210 degrees.